All right, today I'd like to finish up our discussion on increasing, decreasing maximums and minimums. Okay? We've done a few examples the last couple of days. I need to do a couple of more examples that are just a little different from the ones we've seen up to this point, and then I think we'll be ready to move into the next concept. Okay? The first example we'll work here today is this one right here. The quotient where x squared minus 6x plus 9 is the numerator, and x plus 2 is the denominator. And our goal or our question is still the same as what we've done before. Where is this graph increasing? Where is it decreasing? Where are their maximums? Where are their minimums? Okay. All right, we start by looking at the graph, and we're looking for critical numbers. And from this equation, where do we have a problem in terms of just a domain here? Negative 2 is a problem, right? If we try to sub that in, we'll get division by 0. So definitely negative 2 needs to be a critical number. Okay? Are there any other critical numbers? And the answer is no. Other things to look for besides division, things that we can also check for in terms of discontinuities, we can look for, is there any square roots in the function? And of course there isn't. Are there any logarithms? And again, there aren't any. So since we don't have any of those other places that give us problems on graphs, this is our only critical number, at least from the discontinuity side. Now, second place we get critical numbers is when we set the derivative equal to 0. And so let's go ahead and do that. Let's take the derivative of this function, see where it equals 0. Okay. The rule I need to use here, of course, is the quotient rule. And so let's walk through the quotient rule. Okay. The first part of the derivative says I need to take the bottom piece times the derivative of the numerator. And the derivative of the numerator is what? 2x minus 6. Okay, subtraction on the quotient rule. I need to rewrite the numerator and take it times the derivative of the denominator, which happens to be just 1, all divided by the denominator squared. And my goal is to set this function equal to 0. Whenever we have a fraction and we're trying to set it to 0, do we need to worry about the denominator? No, because if I can get the numerator to turn into 0, 0 divided by anything is 0. So in my mind, I can just ignore this x plus 2 squared. Let's do some distributive property up in the numerator, and let's start cleaning this numerator up here. Okay? Here I've got 2x squared. Here I've got minus x squared, so it looks like I have a total of how many x squareds? 1, right. I've got 2 of them here, minus 1 of them here, so I have 1x squared up in the numerator. Okay? If I look at the x terms, here I have a negative 6x. Here I have a positive 6x, so those are gone. Okay? And here I have a what? 4x, and so I end up with a total of 4x. Okay? In terms of the number, okay, just regular old constant numbers here. Here I have negative 12, and over here I have negative 9, so that is negative 21. Okay? And again, I'm not going to write the denominator because that part doesn't matter. I just need to make the numerator turn into 0. Again, most textbooks are pretty nice. They will give you stuff that can factor at this stage. Let's factor this into two binomials here. What are the magic numbers this time? 7 and 3. Two numbers that multiply to give me 21 that are 4 units apart. And what about the signs in here? Plus 7 and a minus 3, that's how I get my positive 4. Sure. Okay. So my two critical numbers from this problem, negative 7 and positive 3, and I join that together with the critical number from before, so I have 3 critical numbers on this particular problem. Okay. Now, from here, this is where we set up our interval. Okay. So we imagine our number line. The first interval will be from negative infinity to the smallest critical number of the 3, and in this case that happens to be negative 7. Then I go from negative 7 to the next smallest critical number, which happens to be negative 2. And then from negative 2 to 3, and then from 3 on to infinity. Just listing out, breaking the interval up at the critical numbers. Now I need to pick a point in each of these intervals, test it into the derivative, and see what value I come up with. And again, I only care about is it positive or negative, because that'll tell me if it's positive, I've got an increasing graph. If it's negative, I've got a decreasing graph. Okay? So let's pick a number in here, like for example, negative 10. I go back to my derivative. Now, I probably don't want to use this piece because this is unsimplified. I may want to just come down to this piece or even this piece. Factored forms are the nicest to sub numbers into. Okay? Do I need to worry about subbing into the denominator? Well, typically the answer is yes. But on this particular problem, notice my denominator is something squared. And what type of numbers do we get when we square? They're always positive. So I will always be dividing by a positive number in the denominator. No matter what I choose to sub in, I'll always be dividing by a positive, and is that going to change the sign? No. Now, we've got to be a little careful though. If this would have been a cubed, for example, we did all of our simplifying and it turned out to be cubed, then I've got to remember, I've got to sub that negative 10 into the denominator as well. Because this time I might get some times where it's positive and other times where it's negative. Okay? But for our example, we don't have to worry about it because everything's positive in the denominator. Okay, so I pick negative 10. I sub it into here. Negative 10 plus 7 is negative. Negative 10 minus 3 is negative. Negative times negative is positive. So I have a positive numerator. I have a positive denominator. So what's happening in this interval? It's increasing because I have a positive slope the whole time. Now I choose a number in this next interval. Okay, I'll choose negative 5 as my number. If I sub in negative 5 here, this is what? Positive. This is negative. So the numerator is negative. The denominator we said was positive. So the whole quotient is negative. So what's happening in here? Decreasing. Okay. I'll back up here before we continue on. What's happening right at negative 7? Maximum. The graph was increasing, then it got to negative 7 and it started to decrease. So that means right at negative 7, we have a maximum value. Okay? And we'll find out here just shortly what that number is. All right, picking a number between this interval, negative 2 and 3, I'll pick 0. Okay? 0 plus 7 is positive. 0 minus 3 is negative, so the numerator is negative. Denominator is positive, so what's going on here? Again, it is decreasing because my whole quotient is negative. And then the last one I have to pick from 3 to infinity. I'll pick 5. If I sub in 5 here, positive. 5 in here, positive. So this time it'll be increasing. Okay. Notice I didn't look for maximum or minimum right here because it was decreasing and then it's still decreasing. Right? So there's no change. I don't get any maximum or minimums there. Okay. What's going on at 3? Okay, that should be a minimum, right? The graph was decreasing and then started to go back up and increase. So it looks like we have a minimum right here at x equals 3. By the way, just to talk about this, what is going on at negative 2 in this example? Look back at the original problem. What's happening at negative 2? Okay, I get division by 0, and so one of two things is happening. It's either a hole in the graph or else it's a vertical asymptote. And the way that I tell the difference between those, if I sub in negative 2 up into the numerator as well, if I get 0 divided by 0, there's a good chance that this is a hole in the graph. If I get something else divided by 0, then it's a vertical asymptote because then I don't get that factor to cancel off anymore. Okay? So if I plug in negative 2, do I get 0 up in the numerator? Well, negative 2 squared is 4. 4 plus 9 is 13. Negative 6 times negative 2 is 12. 13 plus 12 is at 0. Well, no, definitely not 0. So I have something else divided by 0. So that's a pretty good clue that this number is really a vertical asymptote, okay, within my graph. All right, now I want to go through and rough sketch the picture of this graph. Okay, we have enough information here where we can draw a pretty good picture of what this graph looks like. Then I'll have you plot it on your calculator and see if we did a good job. Okay? Before we start graphing, though, it would be nice to have an idea where this maximum is at. We know that it occurs at -7, but what we don't know is the y value. Is it -7, -3, like right down here? Is it -7, 100, making it be way up here? It'd be nice to have a decent estimate of what that y value is. So let's go ahead and take -7 and plug it into the original, and let's see what we come up with. Okay, let's get a rough idea what that y value is. Okay, -7 squared, 49, plus another 9, 58. -7 times -6, 42. 42 plus 58, 100. So my numerator's 100. -7 plus 2 be -5. So what's 100 over -5? -20. So this, like I said, just gives me a rough idea. I know it's not way up here. I know it's not even this high. -7, wherever it's at, -20 is the location of that maximum point. And that seems a little strange that a maximum value is this low, but it'll work on our graph. Okay? Let's do the same thing for this minimum point over here. Let's find the y value of it. So x is 3. If I sub in 3 here, 3 squared would be 9, plus another 9, 18. 6 times 3 is 18, so this will be 18 minus 18, so it's actually 0, isn't it? Okay, 3 plus 2 is 5, so 0 over 5 is 0. So my minimum value is actually 3, 0 over here. Okay, so I just sub in the coordinates. Okay. All right, we said -2 is a vertical asymptote. So wherever -2 is at, we can draw that in. Okay, and I think we've got enough information here now. We can draw a pretty good graph of what this looks like. Okay, before I get to -7, the graph needs to be increasing. Okay, so I have to start out somewhere way down here and let it increase until it gets to that maximum point. Once it gets to that maximum point, what needs to happen next? Well, it needs to decrease. Okay, so it'll probably just go off down toward that asymptote there. Okay, now the other side. I need the graph to be decreasing, and it needs to hit a minimum value. So where do I need to start? On the opposite side of an asymptote, I either need to start up here or I need to start down here. Where do I need to start here? Top or bottom? I have to start at the top because I need to be decreasing right away. And if I start at the bottom, I can't go down any lower. Right. So this graph will actually jump ship, and it'll be -infinity, and then the other side it'll be positive infinity. Okay? It'll be decreasing until it gets to this minimum point, and then it will start to increase once again. Okay? And so really rough, this is a picture of what this graph should look like. And if you want to punch it in your calculator, make sure you put some parentheses around the numerator and denominator. But that graph should match up or look somewhat close to what we have here. Okay? The big advantage of the calculus, why can't I just take this and plug it in right away and see the solution? Okay? Well, let me show you what will typically happen. And I'm going to go to my screen over here. Okay, up in the numerator, I've got x squared minus 6x plus 9. In the denominator, I've got x plus 2. Showing up very well today. And I'm going to do a zoom standard because usually that's where we start, is we just start with a standard graph. And this actually looks pretty decent for half of our graph, doesn't it? I mean, this matches up pretty good. It looks like we hit around 3 and then go back up. Okay? But what's missing from this graph? Well, we're missing this other branch down here, aren't we? Okay? And that's why we have calculus in place, or that's a small reason, but it's a reason that we would go through all this work, because if we were just to graph this, we might think that the whole graph is right here and that's it. We may not know there's another branch to this graph somewhere else, and it's actually way down off of our screen. Okay? If I was to change my window, of course we know that this value is -20, so we actually have to pick numbers even smaller than -20. So let's pick my y minimum to be negative 50. Okay, just change this value. Now if I graph this, now I start to see the other branch. Okay, and if I want to see a little bit better picture, I could adjust my window a little more, okay, to see that this will actually continue to go back down. We just can't see it right now because our X minimum isn't small enough. Okay, and if we wanted to see a little better picture of that curve up on the upper right side, we could adjust our window appropriately. Okay, so that's the advantage of being able to go through and use this. I mean, yeah, you can graph it on your calculator and you can find these minimum coordinates right away. You've got a function built in on there to do that, but you may accidentally miss a branch of the graph, and that's the reason we have this in place. If we can find those critical numbers, those will help us find any of those missing pieces to a graph. Okay? All right, the last example I'll do here today is going to be an application, a word problem type example here. Let me go ahead and put it up on the screen here so we can read what it's discussing. Okay, in this book, this will be question number 41 that we'll look at. Stay there. Okay. It says, suppose that the cost function for a product is given by this equation. Find a production level, in other words, the value for X, that will produce a minimum average cost per unit. Okay. So there's our setup. The thing that I want to teach you is how to break down these word problems to see really what is this asking for. Okay, mathematically, what is this saying? Okay, what's the one key word that you hopefully will pick up on this last sentence down here? Produce the what? Minimum value. So all we're after is a minimum value here. Okay, and we know that we find minimum values by taking the derivative and setting things equal to 0 and then doing our increasing and decreasing stuff. Okay. So that's all this question is really after. Now, what equation do we want to find the minimum for? Well, it says produce the minimum average cost per unit. Okay? They have given us the cost equation. They want us to find the minimum on this equation. Okay, so this is where we got to be a little careful. How do we write that average cost equation? How do we write that C bar of X equation? Well, if I have a total cost of $1,000 and I have 10 items, how do I find the average cost? Sure, just divide by 10, right? Just divide by the total number of items. So if I have an unknown total cost, C of X, what do I do with this C of X equation to find the average cost? Divide by X, right? Divide by how many ever items we're talking about. Exactly. Okay? So that's a formula. We saw it earlier this semester, but it's been a little while. So if you ever want to find an average cost, just take your function and divide by X. Okay, we're just splitting up the cost among all the X items. Okay, now I want to take the derivative of this thing. Okay, getting into a lot of messy notation here. C bar prime. Okay, we're taking the derivative of the average cost function. Okay, I need to use what to do this? Well, I could use the quotient rule. Okay, as one possibility, or I might be able to do a little bit of algebra to clean this up and then I don't have to do the quotient rule. Okay, so I want to show you this little trick here. So before I do the derivative, let me erase that first. Okay, let's just simplify this. This X is a common denominator, so it actually can be divided into each one of the three pieces. So what if I take this first piece and divide it by X? 002x squared, right? What if I take X into the second piece? Minus 9. And what if I take X into the third piece? Well, it would just be 4,000 divided by X, right? But if I want to take the derivative, how do I easily take the derivative of 4,000 divided by X? How would I write it? 4,000 X to the what? Negative 1. Let's go ahead and move that X up into the numerator. Now I don't have to do any quotient rules. It's just a whole bunch of just normal old power rule derivatives. Okay? All right. So now let's go ahead and take the derivative. Derivative of the first piece. What is it? 002 times 2 would be 004, right? So 004 x to the first. The derivative of negative 9, 0. The derivative of this is what? X to the negative 2, sure. Okay, so much easier derivative if I do a little bit of algebra to clean it up initially. Okay, now, if you don't notice this and you do the quotient rule and do all your simplifying, you will eventually get to this same place. Okay, so you're not doing anything wrong if you don't notice the algebra. Okay, I want to set this to 0. And when I'm ready to set it equal to 0, I probably want to rewrite that as a positive power again. Okay? It's just a little easier to do computation with positive numbers. All right, what do you recommend we do to solve this for x? There's more than one way to go about it, but what's one possibility? What could I do with this term? Could subtract it over to this side, sure. Okay, so negative 004x. Okay, next what would you do with this denominator? Multiply it across, cross multiply, sure. So negative 004x cubed equals negative 4,000. Next, divide off the negative 0.004, right? Okay. And let's go ahead and get that number here. Oh, I could probably figure it out if I thought about it, but I'll let you do it. What's negative 4,000 divided by negative 0.004? 1 with how many zeros? 6 zeros? Okay. Okay. And then how do I solve for x? How do I get rid of this third power? Third root, right. Okay, so I need to take the cube root of 1 million. 1, 2, 3, 4, 5, 6. And the cube root of 1 million is a pretty nice number. 100, yes. Okay? So x equals 100 is my critical number. Okay? Now, we can pretty safely assume that this is the minimum value that they are really after. Okay? But if we want to be on the safe side, okay, just to make sure, what should happen if this is really a minimum value is that the graph should be decreasing and then it hits 100 and then it goes back up and increases. So we can pick a number just to the left of 100, like we could pick 99, okay? Try it in the derivative and see if it is a negative value. Because if it's negative, that would mean the slope is decreasing, or the graph is decreasing. Okay? Then I could pick a number like 101 on the other side, plug it into the derivative, and make sure that it's a positive value. Okay? And if that's the case, that would be our proof or our verification that, yeah, that's really a minimum value. Okay? All right, we'll see you next time.